Hello everyone. In this session we are going to show how to make some calculations with the singular value decomposition using some computer programming. So here I use Octave, but the same, exactly, almost identical actually, functions that you can use also with Matlab, because Octave is open source clone of Matlab, but it is free, of course. Matlab, you know that it is somehow expensive for getting license, but here we can use it for free, and you can download it from octave.org. This version is 6.1. Yes, we will show how to make some calculations with Octave to calculate the singular value decomposition, and we will see also some applications of the singular value decomposition. As we mentioned in the theoretical sessions, that there are a lot of applications of singular value decomposition. For example, just we show there is one prize given by Netflix to improve the rating of customer that they are watching movies, and the winner used singular value decomposition and they got $1 million for that. So this shows the importance and the applicability of singular value decomposition to handle very difficult problems and challenging problems, because actually what Netflix had at that time, it was, I think, in 2009, they had about 500,000 customer, and they had also 17,700 movies, and not every customer has, of course, rated all movies, but they have about 100 million rating in that very big, I think the size was several billions in that matrix. So it is very huge matrix, very big matrix, but in the same time it is a sparse matrix, since there are a lot of zeros in that matrix, so that the non-zero elements was maybe 1% or even less. And it was a really challenge to find algorithm which can improve the accuracy or the prediction of the customer rating based on certain movies. And actually singular value decomposition was able to improve the prediction with about 10%, which is very big improvement at that time. And maybe some ask why Netflix should pay that much money to get that improvement in rating, because actually even 1% improvement in the prediction, it makes a lot of money for Netflix as like profit, or increasing the profit of Netflix based on that good prediction or more accurate prediction of what customers want to see or to watch. So it is very important from the business point of view, but for us it is important also to show that the singular value decomposition is very sophisticated method, even it is quite simple, and however that it can manage with huge data. As also we mentioned, of course, you can before I continue, you can read a lot about this and how the winner were able to utilize the singular value decomposition to achieve the requirement, and why they win that prize, and compare them with the other proposals at that time. So there are a lot of material that you can find by googling it. So we also mentioned some other applications for singular value decomposition for deep learning, and for example, the principal component analysis is one of the most important applications of eigenstructure of matrices. And this is, of course, the general like umbrella is eigenstructure or eigenfactorization of matrices, and this is it has many applications when we talk about column space, null space, and row space, and so on. So they are important to digging deep in matrix and to see more information inside matrix. And now it just came to my mind that in beamforming, for example, in beamforming, we utilized this eigenstructure of the matrix in order to find the number of transmitting antennas, and also if there's jamming, then we can also determine the direction of arrival of the jammers and so on. So it has applications in telecommunication, applications in machine learning, in deep learning, in linear algebra in general. So too many applications for the singular value decomposition, or in general in the eigen decomposition. But why we talk here more about singular value decomposition? For one reason, that it is a general method, so it can work with square matrix or non-square matrix. It can work with like real number matrices or complex matrices. It is very general method which can be applied in many different applications. Okay, let us go to the to Octave now, as you can see. And of course we can work directly in the command window, or we can write our function in editor, and then we can write many times. But before I do that, let us go to the command window. So I just, for those who don't know Octave, I will show a few things here. For example, we if you want to build or to write a matrix, then you can, for example, it is A, so we open it in this brackets. So we can write, for example, if we want to generate matrix 1, 2, 3, and maybe 4, 5, 6, so that's all. So now we have this matrix. And if you want to take the transpose, then it is, you just make dash, then you take the transpose. If you want to multiply A by its transpose, the matrix multiplication is just the star. So, okay. So if you want to calculate the singular value decomposition, then you can just write, for example, the U matrix and maybe the diagonal matrix and V matrix, and then you write just singular value decomposition SVD, and you put A. So you get you can see here that you can get the U matrix, and this is the diagonal matrix. This is the non-zero, and the third one is 0. Of course, it means that the rank of this matrix is 2, and then the V, or the row space matrix. And if you don't want to see the result directly, so you just add semicolon this way, so you don't print out the result in the command window directly. However, it is computed, of course, in U, D, and V. Okay. So this is just general review about how to write matrices and to compute things here in Octave. Okay, now let us go to the editor, and we start with clear all, which means that I just remove or clean Octave for all parameters, and then we can define any matrix. So let us start with A equal to, and well, okay, 1, 2, 3, maybe 4, 5, 6, 7, 8. Sorry, 7, 8, and 9, 10. 9, 10, 11, 12. So we have only 4 columns, but we can have many, for example, rows. So I can say, for example, okay, 1, 1, 0, anything actually I can add, 0, minus 1, minus 2. Okay, what else? Maybe 10, 12, 14, and 16. Okay, 16. So all these matrix together. Okay, and now we can calculate the singular value decomposition. So you can, of course, put any names that you want, U, D, and V equal to singular value decomposition SVD of A. Okay, Now we should save this script. So okay, so we give it any name. Maybe we can call it like deep learning, deep DEL1. Okay, and let us save it. Okay, now we can run it here. So you can just put run, and now uh, okay, it seems that we have something wrong in the implementation. Let us check that to be sure that we have 4 elements in each row. So 1 2 3 4, 1 2 1 2 3 4, 1 2 3 4, 1 2. Yes, here this is the problem. So here we have only 3 elements, so it should be 4 elements. 1 2 3. Also here we have problem, so it should be like 4 elements. 2 3. Yes, now it should be okay. Save it. Okay, now we can just run deep learning 1. Okay, it is executed now. Since it is executed, you can see now what is A. This is A that we generated. 1 2 3 4 5 6 7 8. So you can see here actually we have how many columns. We have 1 2 3 4 columns, and each column it has 1 2 3 4 5 6 elements, which means that it is from R6, from real number of dimension 6. Okay, so what we can see here, if we look to the decomposition of this matrix with the singular value decomposition, so now we have the matrix U. So what do you think that will be the dimension of matrix U? Yes, the dimension of matrix U should be 6 by 6. Okay, by the way, you can read the size of any matrix in Octave by just writing size of, for example, of A. So you can see that it is 6 by 4. If you write size of U, it is 6 by 6. Size of V is 4 by 4. Okay, what do you think the size of D should be? Yes, it is 6 by 4. Yes, so D is 6 by 4. Okay, now if we look to the matrix U, this is the matrix U, as you can see. This is the first column. Now they are called eigenvectors. So we have the eigenvector, the first eigenvector, the second eigenvector, the third eigenvector, up to the sixth eigenvector. Okay, and what do you think about the matrix D? The matrix D is 6 by 4, and the original matrix A is, the size is 6 by 4. If you remember from the theoretical session, we said that the rank of the matrix must be less than or equal to the minimum of the number of columns and rows. Here the minimum number is for the columns, and it is 6. It is 4, which means that the number, the rank of this matrix must be less than or equal to 4. Okay, so if all 4 columns are linearly independent, then the rank of this matrix will be 4. If all the ranks of or all columns and all rows are independent, then we will have rank 4. If we have dependency between those rows or columns, then the rank can be less than 4. How could we know the rank of this matrix? It is the number of non-zero singular values. The number of non-zero singular values. We know that the singular values, the matrix D is a diagonal matrix. Diagonal matrix means that all elements are zeros except in the diagonal. So the number of non-zero elements in diagonal, it gives us the rank of this matrix. Okay, let us see the singular values now, the diagonal singular values. Of course, you can just write D like this. Okay, so we have 1 2 3 4, so we have 4 non-zero singular values, which means that this matrix has rank of 4. Okay, we can do it in different way. If we write just, for example, d small equal to diagonal of d, it gives you directly just one vector with the diagonal elements. Okay, if you remember also from the theoretical session, we said that that the singular value actually represents the number or the information of the eigenvector. For example, if you look to the first singular value is 36.6, which means that the first eigenvector in U matrix contains most of the information in this matrix. Most of the information. Actually, if you divide 36, if we divide, for example, if we take like d1 divided by d1, it will reflect only the first element, divided by sum of d, it will give us the percentage of d1. If we divide it over all d, you can see that 88.79 almost. Of course, it is just a rough estimate that about 88.8 percentage of the information is just allocated in the first rank or the first singular value, singular eigen vector of matrix U, and of course in the first row of V transpose, of the matrix V transpose. As you can see, 0.365, it means that the fourth, sorry, 1 2 3 4, so the fourth column or the fourth eigenvector of matrix U, as well as the fourth eigenrow in the matrix V transpose, it has very little information about the original matrix A. It has very little information about the matrix A. Okay, now what about the others? I mean, here we have the fifth column and we have the sixth column. Actually, the fifth column and the sixth column, it is called null space. So it has no information about the matrix A. So we can reconstruct the matrix A, fully reconstruct the matrix A without any knowledge of the columns fifth and sixth, because they will project any multiplication with vector x into the null space, and this null space is orthogonal to the column space. Okay, let us do something interesting here. So if I want to construct a matrix A by using only the most of the highest information in the first eigenvector U and first eigen row V. So how can we do that? Is very simple. So I will call it x1. Okay, x1 equal to, we take only the first column. It means that when you put two dots like, sorry, when you put two dots like that, it means that all rows, but we take only the first column. Okay, we multiply it by d1. It means that the first element or the first singular value, if you want to use the matrix D capital, so you can put 1 and 1, it is up to you, times V transpose of the first row and all columns, simply like that. Now this x1 actually is a reconstruction of the matrix A, and it should contain most of information, but it is not perfect. It is not all information. If I want to construct all information, I should use all these four elements. But now, by taking only first column and first row, I can get. So you can see here. So this is what we have obtained by using this multiplication. Okay, so this matrix actually contains most of information in the original matrix A. Okay, if you want to take the more information, we can generate also x2, for example, x2, and x2, it will be the second column the second element here and the second row. Okay, so this is the second element. Okay, if you add this x2 with x1, you will get better approximation. So x1 plus x2, you will get better approximation. And even if you add the other elements, of course you can get better and better approximation for the original matrix A. Okay, so this is the concept here, how to calculate this or how to make some computations of the matrix. In the second video, I will divide this into two videos. The second video, I will show some practical application. So I will upload one image and we try to make compression by using this singular value decomposition, decoding, coding, and decoding in simple way. Okay, thank you and see you in the second video. Thanks.